Okay, here we are, third podcast of the Solutions Unit, talking about solubility rules. We are filling in the top itty bitty little bit of page 9, and then you're going to be working on page 10 on your own, and I'm going to do one example from there to help you get started. So this is what I'm talking about, page 9, just this part, and then you're going to do all of this. Well, technically I'm going to take off a couple of problems, but that will be up to you. So let's get going. So what we're talking about here is solubility rules, how we can tell if something is soluble. And we sort of misled you earlier when we said that all ionic compounds were soluble, back when we were talking about what would dissolve in water or not. It's a little more complicated than that, but we didn't want to get ahead of ourselves. So with covalent compounds, we have to ask ourselves those two other questions about, does it have the lone pairs on the central atom or different elements around it? But if it's ionic, we have to look at the chart on the back of our periodic table to figure out if something is soluble or insoluble. And we've seen these words before, but just as a reminder, soluble means that it's dissolved or it can dissolve in water, which is something that we're going to see generally in a chemical reaction be marked as aqueous if it is dissolved in water. So one's kind of is it, one is kind of can it, but they still kind of mean the same thing. Insoluble means that it would be a solid, be marked as an S more than likely in a chemical reaction. So one other special word that'll go with those chemical reaction solids is precipitate. If a solid is formed, one of our products is formed as a solid, then that would be a precipitate, and that's going to be important on the next page. So really what this comes down to is looking at the back of our periodic table. And we don't need those two parts on the left and right that we've already looked at, the polyatomic ion list and the activity series. We're focused on this chart in the middle. And the whole thing is our solubility chart. Notice that there's this section here that says soluble. All of these things underneath it, these are anions, negative ions for the most part, which means that they tend to be at the end of a compound's formula. But if you see a compound that ends in one of these things, then most of the time it's going to be soluble. You'll notice, though, that over here we have some exceptions to those soluble anions. So things like Br tend to be soluble, tend to dissolve, except when they're with these three specific things. And those three specific things are also exceptions for chlorine, but then iodine has some extras that are a little bit different, but some that are the same. So you always have to check this list. You're always going to be able to use it. It's on the back of your periodic table. We just need to look at the end of our compounds, where it's at in these lists, see whether it's soluble, or down here we have that insoluble section, which also has exceptions, and figure out where it falls, make sure it's not an exception, and that's going to tell us whether we're soluble or insoluble. So I want to point out down here real quick that the insoluble has some exceptions that are exceptions for every single insoluble compound. So these are things that will make every single compound soluble, and that is our alkali metals. So I like to list those out kind of off to the side, maybe highlight those all in the same color, and then make a note of what those alkali metals are so you don't have to flip back and forth. They're just the first column of elements, minus hydrogen, of course, because it's not a metal. But anytime you see any of those elements at the beginning of a compound, those are automatically going to be soluble, just because it's an exception to everything that could possibly be insoluble. So there's some other things that you see up top in this soluble section, like nitrate is soluble, and if you follow that over, there is nothing that is an exception, so nothing is going to make it insoluble. So that's how we're going to use it. Some other marks that I like to make on here, which could be a little bit redundant, but it kind of reinforces what we wrote on the previous page. I just like to write this S here, mostly so that I can follow it up with this I here. So I explicitly state this is the soluble section, but if I get dragged over into this exception area, that's insoluble. And down here I have my insoluble section, and the exceptions are soluble. Sometimes I even write those states of matter because soluble means it can dissolve. If it's in a reaction, it probably is dissolved. It's marked as aqueous. And those insoluble things are our solids, which we could also call precipitates. So this is how I like to mark up the back of my periodic table so that when I'm looking at these formulas, I've got everything that I need right there. So remember, what I mentioned is that these lists, this is where we're starting over here on the left-hand side, and we're going to be looking for the end of our formula in that list. So with this first one, NaCl, I see Cl is right over here, which makes me think that that's going to be soluble, but I need to check and see if Na is an exception. So if I follow that over, Na is not in this row. In fact, it's one of those things that's always going to be soluble. So because of that, this is a soluble compound. NH4OH. Start by looking at the ending bit. This OH, this hydroxide, is actually down in the insoluble area. So I'm thinking that this might be insoluble, but if I follow that over, the exceptions, one of the other things that's an exception in every single insoluble section is this NH4. This ammonium is always going to make things soluble. So we've got that there. And then BaSO4. I'm finding the SO4 part. You'll notice these do have charges on them in the list. We don't see the charges here because they're hidden. That was a Ba with a +2. So the SO4 with its -2 kind of got hidden in there. But it just looks the same way it looks on the polyatomic ion sheet. So SO4 tends to be soluble, but I have to check for that Ba over here in my list, and it is there. So that pulls me over. I am not in this section anymore. It pulls me over into this section where I am insoluble. Not too bad, right? The more familiar you get with this chart, the easier it's going to be. Remembering to start from the end is going to save you a whole lot of headache too. So next column, AgCl. I should be starting by looking at the Cl. Cl is in the soluble section, but if I follow this over and look at the exceptions, Ag is an exception. That makes this insoluble. SO4, aluminum is not an exception, so that is going to be soluble. OH, NH4, actually I think we've seen this one before, so no surprise that it's soluble. Next column, Na3PO4. I've got my PO4 down here. That makes it look like it's insoluble. And when I follow this over into the exceptions, I don't see sodium written out explicitly there, but you have to remember sodium is an alkali metal. So if you didn't write those down, you might say that this is insoluble, but because it is an alkali metal, that pulls this over into that S area, the soluble section. I made a big old mess here. Next one, magnesium carbonate. Carbonate is the first thing in that insoluble section, and magnesium is in the second column, not the first, so it does not count. It is not an alkali metal, so it is not an exception, which means this is insoluble, follows the rule. PbI2. I is here, it's soluble, but if I follow that over and look, Pb is an exception, which means that it is insoluble. Hopefully these are getting easier and easier. We got one last column to do. I am going to finish these out just because I don't want to leave you alone. So I'm finding the ends of each of these formulas. OH is over here, and oop, that's a Ca, not a Cu, I think. Mine's a little bit small, but double check yours. But because Cu, copper, is not over here, then the rule is that it is insoluble. Pbs, S is insoluble, Pb is not an exception, so it remains insoluble. Potassium carbonate, carbonate is insoluble. Potassium, though, is a sneaky little alkali metal, so that makes this soluble. So that's really all that there is to it when we're looking for an ionic compound to tell whether or not it is soluble or insoluble. But, of course, it's not always going to be quite that simple. At the top of page 10, that question number 1 has that whole big kind of section of formulas is exactly like what we just did, except it wants you to circle things that will not dissolve in water. So that means circling things that are insoluble. And I'll remind you later, but there are 8 circles up in that section. Now, question number 2 has reactions that you have to write out and balance, and then find the precipitate, which is the insoluble thing. So we're still circling the insoluble compounds, but we have to find the compounds before we can circle them. So let me remind you that with a double replacement reaction, the chemicals are going to rearrange, and the first thing from this compound is going to get together with the second thing from this compound. And then this is going to get together with that. So the second one and the first one. So we're mixing and matching. This is the wife swap reaction that we'd seen before. So I'm going to put, we circle the precipitate. I already said that. Great. So calcium and phosphate are getting together, but remember, anytime we put things together, we have to check the charges. Calcium's in the second column, so it gets a +2 charge. Phosphate on the back of the periodic table is a -3. Because they don't match, we're going to have to cross drop reduce, and that means putting some parentheses around that PO4. So this is my first compound. Then we have to take the leftovers and make it my second compound, and making sure that that Li goes first. I know it's in the second compound, but it was at the beginning of its formula. It needs to be at the beginning of this formula too. And luckily for us, when these charges get checked, I have a +1 and a -1. So that's actually stable together just like that. So I have predicted the products. I need to balance the equations. So first thing I'm seeing is 1 calcium over here and 3 over here. So I'm going to go ahead and put a 3 over on this side. That gets me 6 nitrates as well, with this 3 and the 2 on the outside of the nitrates. Remember, you can keep this nitrate as a group because I've got more nitrates over here. But to get 6 nitrates with the 3 and the 2 multiplying together, that means I need to put a 6 over here. Next thing I see is lithium. There's 3 on the reactant side and 6 on the product side, so I put a 2 here, and then everything is balanced. So, predicted product, balanced equation, and now I need to circle the precipitate. So, going back to my formula sheet, my equation sheet, I'm going to start with this first thing, calcium phosphate. Phosphate is here. Looks like that's my insoluble thing, and calcium is not an exception, so that looks like my answer. I'm just going to double check and make sure lithium nitrate isn't, and nitrate, like we've seen before, is soluble, and there is nothing that will make it insoluble. So the thing that is my precipitate is that calcium phosphate. So that's my answer. So these really aren't that hard. It's bringing back a whole lot of old skills for these reactions down here, but I know they take you a little bit longer, so I'm omitting these 2, and I'm going to help you right now with getting this E started. It says that we have lead 2 nitrate to be precise. So that means that my lead has a +2 charge, which means it's going to be crossing over onto that nitrate, because nitrate just has a -1. And then sodium bromide is sodium and bromine, and they are +1 and a -1. So helping you put those together, because I know those Roman numerals can be scary, getting you to basically the same starting point as the rest of those. So good luck with them. Like I mentioned before, you should have 8 circles up here in number 1 when you're circling those precipitates, things that do not dissolve in water. And I have posted what the precipitates are for each of them. We've already done this one, so you just should be checking your work for these 3, writing those reactions, balancing them, of course, but then I have the precipitates, because that's really our goal here. If you can get that right, we can work with everything else. So that's our solubility rules for ionic compounds. Thanks for listening.